Today we will continue our discussion on flow sensor. In last lecture I remember I have introduced the flow sensor, and there are two basic techniques of measuring the flow of the fluids, and those two techniques will be discussed in details, and some of the experimental results and some of the design aspects of the flow sensors also will be discussed. Now, there are two techniques which are used for designing micromachined flow sensors are namely thin film anemometer principle, and other one was differential temperature technique. Both of the flow sensors belong to thermal flow sensor. Basic principle behind this, a heater will be there, and the heat will be dissipated from the heater with flow. If the fluid flows, depending on the flow pattern and depending on the flow velocity, the heat dissipation will change, and because of the heat change, some of the properties of materials are also will change, and that will be the measure of the flow. That means it is not direct flow measurement, it is indirect flow measurement. Flow pattern is going to change the heat dissipation in the first phase, and second phase the change of, because of the heat dissipation, the temperature of that particular sensor will change, and that will change the material properties. So, that means it is two-step process. So, out of those two steps, those first one, thin film anemometer, has got certain advantage, disadvantage, but the second one, differential temperature technique, is well acceptable, because there the individual temperature of the heater or sensor is not important, but difference of temperature between the two heaters is important, which will automatically eliminate the environment, lot of environment effect, means the room temperature or radiation from outside sources which are coming onto the sensor. Those effects automatically will be neglected in the second class of the thermal flow sensor, which is differential temperature technique. Now I will directly go to the principle which is based on thin film anemometer, design's perspective of the thermal flow sensor based on thin film anemometer principle. In the design perspective, what is to be done? First, a thin dielectric layer of silicon dioxide of 1 micron is thermally grown on the silicon cantilever. Why this is required? Because if you want to have a sensing element, that is in this particular case is basically a thin film resistance, and directly the thin film resistance if you make on silicon, silicon is also a semiconductor material, it will have certain conductivity. So, that means the silicon as well as the thin film resistance which change you are going to measure, that will be combined phenomena. So, in order to isolate this combined effect, we normally put a insulation layer or isolation layer in between the metal film and the semiconductor material. And semiconductor material, then what is the purpose, you can ask me? The purpose of using the semiconductor material is that we can micromachine that semiconductor material, in particular the region where the thin film metallic resistance is placed, so that its thermal mass will be less. So, absorption of that base material, what absorption? Heat absorption or heat dissipation by the base material will be less. So, whatever the dissipation of the film, that dissipation is only due to the flow pattern. Flow pattern, there is convection, if the liquid or the gas flows over the film. So, there is a convection, and due to the convection the flow will be there. And as I told you in last class also, that another effect of heat dissipation is due to radiation, and that heat dissipation due to radiation depends mainly on temperature. If temperature is very high, then heat dissipation will be more, is a sigma T to the power 4, this Stephen's law you know. So, there is a fourth power of temperature. So, if we restrict the temperature of that sensing element low, so dissipation due to radiation will be minimum. I should not say 0, so it will be low and may be neglected in comparison to dissipation due to the flow. Flow is, that is the convection. Conduction, convection and radiation, these are the three methods by which heat can be dissipated. So, out of that, in this particular case, we want only the heat dissipation should be with respect to the convection of the fluid, convection phenomena, that means the fluid flows over the thin film resistance and or thin film heater, and then accordingly the property will change. But conduction should be as minimum as possible. So, in that case, if I put directly the metal film on the semiconductor, that means the base material or the substrate material also will, there will be a conduction of heat from the thin film to the substrate material, and from there it will be dissipated. That we want to avoid it. That is why it is better if you design the whole thing or fabricate the whole thing on an isolation material, which is, that isolation material is either silicon dioxide or silicon nitride. It will have good isolation property, heat isolation as well as electrical isolation. Electrical isolation is also necessary because you are sensing the current through that thin film resistance. So, if it is placed on semiconductor, so the current will be distributed not on the thin film resistor, it will be distributed throughout the semiconductor also. So, that will also create problem in estimating the actual the current change, and after that you are going to measure the voltage change across that thin film resistance if you send a constant current. Okay. So, for that we have to have an isolation layer, and that isolation layer is made here by a thin silicon dielectric layer, and which is 1 micrometer and is thermally grown on the silicon cantilever. Silicon dioxide provides electrical isolation between the sensing element and the bulk silicon, as well as to some extent thermal isolation also. A very thin membrane is created at the free hanging end of the cantilever, on which the sensing element is placed, that reduces the mass of active area, that just now I told you. Now, this is the structure of the anemometer flow sensor device. So, here you can see here. So, this whole the top surface is a silicon dioxide SiO2, and this is the cantilever over which, from the bottom of that cantilever we have etched silicon, although here is 300 micrometer. So, this cantilever is only 50 micrometer, and in this region you have designed and fabricated this nickel resistance, and for ohmic contact you have used the chromium and gold. There are two end of the resistance is a chromium and gold connected, and this is the bonding pad. The total dimension of the sensor is 10 millimeter. Here is a 8 millimeter, and from here to here another 2 millimeter. So, 10 millimeter, 2.5 millimeter is the width here, and 0.275 micrometer millimeter. So, that means 270 micron is the total thickness here. So, that means total piece of the silicon rectangular which you are using for the sensor is a 10 millimeter cross 2.5 millimeter cross 0.275 millimeter. Silicon membrane is basically this portion is there, 2 millimeter, 2.5 is the width, and 0.5 millimeter is the thickness, this is 50 micrometer here. Chromium gold contact lines is 8 millimeter length, this is chromium gold contact line, and W width of this chromium gold is 100 micron. Chromium is used, you know, I mentioned earlier also that for proper adhesion of the gold film onto the silicon or silicon dioxide substrate is a chromium necessary, otherwise the addition of the gold will be very poor, and subsequent processing the gold may be peeled off from the surface of the silicon dioxide. Similarly, nickel, below nickel also we have to use some chromium layer, which will very thin layer is maybe 100 to 200 angstrom unit, not very large amount. So, that will help adhesion of the nickel with the substrate, which is silicon dioxide below that film. Oxide layer thickness is 1 micrometer. On that you can get it by thermally grown oxide 1 micrometer, and a resistor which is here, the nickel resistor which is placed here. This nickel resistor is 600 micrometer is the length and 60 micrometer is the width and 0.12 micrometer is the film thickness. So, that is the sensing element or the heater. Here heater and sensing elements are both same in case of the anemometer flow sensor, but in other case those two are different. We will explain that also. So, this is the basic design structure of the structure of the thin film anemometer flow sensor. Now, we will discuss on the analytical analysis of this metal thin film resistor, and this resistor is powered by constant current source, is introduced in the fluid medium. That means, a thin film resistance which is put into the fluid medium, either it is a gas or it is a liquid. So, a constant current is sent through that thin film resistance. If the sensing element is in thermal equilibrium with its ambient, then the input electrical power is equal to the power loss due to the convective heat transfer. We mentioned we have to design the total thing so that the heat transfer is mainly due to convection. Convection, what? Fluid flow. Now, when it is in thermal equilibrium, if the power through the resistance is I square Rw, Rw is the resistor value of the resistance of the metal thin film, which is nickel there, I square R the power. Now, this must be equal to H into Aw into Tw minus Tf. Okay. So, this H stands for the heat transfer coefficient of the film, Tw is the temperature of the film, and Tf is the temperature of the fluid. So, Tf is the temperature of the fluid and Tw is the temperature of the film, and H is the heat transfer coefficient of the film. Rw is the resistance of the nickel resistor, which is the sensing element, is Rw. And now, some other parameters are mentioned here as alpha. Alpha is the thermal coefficient of resistance. R ref is the resistance at the reference temperature T ref. The film resistance Rw is also a function of temperature. According to Rw is equal to Rf 1 plus alpha Tw minus T ref. So, Rf and T ref are the reference. That means, if you use the reference is room temperature. So, there. So, after that the Rw, which is the film resistance, will change according to this relation, where alpha is known as the temperature coefficient of resistance. And I mentioned also temperature coefficient of resistance should be very high to increase the sensitivity of the device. So, these two relations in later on we will solve to find out the velocity. Heat transfer coefficient H is a function of fluid velocity Vf according to the King's law, and this is the King's law. Here is the King's law, this one is the King's law. So, that is what H is equal to A plus B Vf to the power C, where A, B, C are constants, which will be found out from the design structure and physical parameters, and Vf is the velocity of the fluid and H is the heat transfer coefficient. Now, the H is equal to A plus B dot Vf to the power C, that will be equal to, in the earlier equation, if you see in this, sorry, here, yes. So, you can see this equation I square RW is equal to H dot AW TW minus TF. So, this equation H will be given by I square RW divided by AW TW minus TF. So, there the H value is substituted here, you see, then you are getting I square RW divided by AW TW minus TF, and which is again in the second equation RW is put, because the second equation RW is equal to RF, R reference into 1 plus alpha into TW minus T reference. If you put this value here RW, the expression looks like this. Okay. So, now the what we did basically here, we eliminate the heat transfer coefficient H, and then if you solve the equation, then fluid velocity from this equation will come like this. Vf fluid velocity is equal to I square Rf into 1 plus alpha into TW minus TRF divided by AW TW minus TF minus A slash B whole to the power 1 by C. So, that is the fluid velocity, which we found is basically the I square R is one parameter, AW the area is known, and the you see TW minus TF fluid temperature and the resistance temperature difference will be there, and we have to have alpha mode to getting more sensitive, and fluid velocity and the current through the constant current which is flowing through the film heater as well as sensing element is related with Vf like that. So, now if you now discuss on the fabrication steps, it will be like that. The starting material which we have started is 2-inch diameter double side polished silicon wafer. Why double side polished? Because you have to align both side, means front side as well as back side also. If it is not both side polished, that alignment will be difficult and it will not be properly done. So, that is why we have to use two side polished, both side polished silicon wafer. It is the N type, resistivity 4 to 6 ohm centimeter, thickness 275 micrometer. Here the type of the substrate is not that much important, because you are not going to diffuse any kind of the dopant into the substrate, or you are not going to make diffuse resistance, you are going to metal thin film resistance, and the silicon is basically the container or is a substrate. Into the silicon you are not going to make any active components or nothing, only the some portion you are going to etch to get the thin structure, and other portion we will keep it as it is, so that the mechanical rigidity will be there. So, now step 1 will be thermal oxidation, which is a normally use dry wet dry, is a 20 minute, 120 minute and 20 minute at 1100 degree centigrade. Silicon dioxide thickness is approximately 1.2 micrometer. Next step is photolithography for patterning of front side oxide, which is grown in step 1 using the front edge mask while protecting backside oxide with photoresist. What did you do in this particular step? Basically, there the front side patterning means the total area of the sensor you are defining. The rest of the portion you are removing the silicon dioxide, so that when you etch backside from the top side also, those layer boundary layer will also etch, so that easily at the end of the process you can break the wafers or break the samples from the wafer easily. Sample means sensor devices, easily you can break it. That is why this step 2 front side patterning is required, and what patterning you are doing? It is oxide patterning, and some of the periphery of that each sensor, some line which is also we call it a scribe line, the oxide is removed. Next is third step, and in third step we do for photolithography, which patterns the backside oxide and while protecting front side oxide with photoresist. This step requires both side top and bottom alignment. So, here in the backside patterning means you are defining the etch area where you are going to make the membrane, okay, as well as the periphery. boundary. That means you can see the periphery boundary of the sensor, either step 2 and step 3 both places you have opened, and now if you etch, then the periphery of the sensor will be etched, KOH will be etched from the top as well as from the bottom, and as well in the from the bottom only the membrane area or the cantilever area it will etch, but top surface it is protected. Okay. So, this is the normally they did the silicon oxide removal for micromachining of the silicon itself. That is these two step they did it. Next is a thermal evaporation of chromium nickel film to form resistors. The chromium film thickness 150 angstrom, nickel film thickness nearly 2000 angstrom. Now, this kind of the chromium nickel, chromium is required for adhesion and nickel is basically your thin film metallic anemometer, that is which is the basically sensing element. So, this kind of structure if you want to pattern, you can face little bit problem. What problem? Because already you have not etched, but oxide you have patterned. Oxide pattern means there on the surface top and the bottom there is some uneven places where you groove you have made it by removing silicon dioxide from the top and bottom. The next phase if you do for lithography, then you may face some problem, because photoresist will not uniformly cover the entire surface and their photoresist thickness may vary over the entire surface top and bottom, and then exposure will not be uniform over the entire wafer, and development and subsequent process you can get some problem. So, for that in this case you can sometimes go for, if you face the really problem, then you can go for the direct deposition of the metal film. That means either lift off technique or you can go for the direct vacuum mask technique, you can deposit chromium nickel film. Okay. And there one advantage is you do not have to bother of the chromium nickel the etching solution, directly you go for that. But if you find that the top surface the scribe lines or etches are not very deep at all, only 1.2 micron or 1 micron silicon dioxide etching will be there. So, you can easily spin photoresist, then you can go for the normal photomasking step, photomasking process, and that is why step 5 is written photomasking of chromium nickel patterning. Then step 6, thermal evaporation of chromium gold film to form the contact. This is the metallization, metal contacts. The chromium film thickness is 150 angstrom. As I mentioned that chromium is basically the adhesion metal with gold and nickel with silicon dioxide, and its thickness is very small of the order of 150 angstrom. Then you go for the chromium gold patterning, that photomasking from chromium gold, and step 8 silicon etching, which is micromachining of silicon with 44 weight% KOH at 25 degree centigrade from back side only, while protecting front side with black wax, and silicon 11 wafer, silicon 100 thickness etched only from the back side approximately 200 micron. That means here what you are doing. So, if you need long time etching, the front surface, since the chromium gold or the chromium nickel has already been patterned on the top. So, the KOH solution may damage the gold or chromium or gold or nickel, sorry, chromium nickel film. So, in order to prevent those damages, normally top side is covered protective layer, and that protective layer in many cases we use the black wax, and on the top of black wax you can, if you press 111 orientate some silicon wafer which normally does not etch by KOH. So, top side will be protected, and from the back side you can pattern, and so that you can get cantilever or membrane. So, after that you remove the black wax and other things, then very thin layer will be there, the separation layer, where that is basically the scribe line. For small amount of time you again you dip it in KOH solution, which will not damage the gold or chromium film, but the silicon will be separated. So, that is normally done, otherwise you have to go for some other the etching technique, micromachining technique, not KOH, those are basically TMEH etching. So, TMEH etching is not available in most of the laboratories, that is why using KOH also people design the process flow, so that easily you can get the complete structure. Okay. Now, these are the fabrication step, and this is the structure, mask structure of the thin film anemometer. So, these are the you see bonding pad here, this is the line, gold line, and this is the resistance, nickel resistance here. Now, there are two kind of design. In one design, the resistor width parallel to the flow velocity. If the fluid flow is in this direction, then this is the width. Width is basically no, this is in fluid flow is along the width of the nickel resistance. This is the this is along the width of the nickel resistance, but width is this direction, along the width is right, along the width of the fluid flow is along the width of the nickel direction, nickel resistor. So, there is another structure where fluid flow is along the length of the resistor. So, and that structure is a second one. You can see here, if you make the design like that and fluid flow in the direction, so that means the flow is in this direction, width is in this direction, so automatically it is in the length. There are two things you can do, flow is along the length or flow is along the width, and here this is along the width. Okay, this is here is the resistance, this portion is the resistance, and here is the along the length, this is the length. So, and both design has been made so that you can measure along the length as well as along the width the resistance change. Okay. Now, here are the complete structure of the sensor lasso layout of the all the masks together here. So, you can see here in each case you can see 1, 2, 3, 4, 5, 6, 7, 8, 8 are the structure 2, and here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 the structure 1. So, both structure 1 and structure 2 has been made, and now you can see the top surface, the white region, this is white and this region basically oxide is removed. So, that here you can etch from the top, and from the bottom you will etch only the region where your film is there. That means, in this particular case film is here, nickel film is here, here nickel film is here, here is here, similarly here in this case, and the structure 1 case nickel film is only in this portion, here is in this portion, here in this portion. So, there from the bottom side membrane is etched, and this white gap between one sensor to other sensor is kept basically for breaking the samples from one to other, which will be easy if those portions are etched from top as well as from the bottom. It will thin down drastically and it is held over some point. For example, here is a joint point, you can see here green, here is a joint, here also is a joint, here also is a joint, similar in this case here is a joint. So, only this joint point it is held with the substrate at the end of the etching. So, that just gentle pressing each of the sensor you can get separated from each other, get separation from each other, so that you can easily go for mounting of individual sensor. So, accordingly mask has been made. Now, here you can see the diagram of the fabricated micromachine flow sensor. Here both the sensor, this is structure 1, this is the structure 2, you can minutely notice here. So, the tip is different color, which is the nickel, and rest of the line is coming the gold, and that is soldered here with some small PCB, so that you can place, you can just cover the whole thing in a tube, and which is fitted in the measurement chamber, measurement setup. So, here also structure 1, here the tip is the nickel resistance, here in this tip is the nickel resistance. So, these are the fabricated devices. Now, the experimental measurements. So, for this kind of sensor you have to go for first measurement is temperature coefficient of resistance of the nickel film, then you will measure the velocity versus the change of resistance. So, first is temperature coefficient of resistance measurement. There what you have to do, the thin film nickel resistance is basically all the measurements are done in ambient environment at room temperature. To increase the temperature, because for TCR you do not need the fluid flow, just TCR means temperature coefficient of resistance, you have to increase the temperature of that particular film and you have to measure the resistance change. Okay. So, that is the objective. So, there the sensor is mounted on a hot plate to measure the change in the resistance due to the change in temperature. Tip of the resistance you put a very strip heater, small strip heater, so that the accurately you can change the temperature and then temperature can be measured with using the thermocouple attached closely to the tip. Then the temperature of the hot plate is measured using the copper constant thermocouple. So, now after that, and the corresponding change in sensor resistance is also measured. The heater you can hot plate basically you can change its power, input power, so that it will be more and more hot, and the sensor is attached to the hot plate, and then sensor temperature will also increase and resistance change is measured simultaneously at different temperature. The temperature coefficient of resistance alpha of the thin film nickel is calculated using the relation which is given here, which is R naught is equal to R reference RF into 1 plus alpha T naught minus T reference, where R reference and T reference are the reference temperature and resistance, and that means reference temperature we assume it is ambient temperature, which on that particular day may be 30 degree centigrade, and at that temperature the resistance of the nickel film is 51 ohm. So, now you put that R naught is known, reference is known, T naught and T reference is known. So, alpha you can calculate easily from this relation. So, the alpha measured value is obtained as 0.006064 ohm per degree centigrade, which matches theoretical value. Theoretical value is nearly 0.0064 or 67 something like that. Up to third order it is matching properly. So, slight deviation is there because the whatever heating I am giving, exact measurement of the temperature of the film is very difficult, because lot of heat loss due to the ambient temperature difference with the heater temperature. If the heater temperature is large compared to the ambient, there will be heat loss due to radiation, and exact measurement of the temperature of the film is not possible. So, that is why some error will come into the picture, and at the same time another deviation is due to, because you are measuring the TCR of the nickel film and you are not expecting that TCR of the nickel film will be as that of the bulk. So, a reported result in the literature is the bulk nickel TCR value. So, that is 0.0064 or 65 something like that, but here we are getting very close to that, and deviation is because of that. Now, these are the measured values of resistance versus temperature, and here you see we have measured for increasing and decreasing both way, because when you increase the temperature, then you can see the resistance value is going to increase, and at the same is a metal, isn't it? So, with temperature increase, resistance value will increase, and again if you reduce it, it will follow the same path, reduce it. So, that value we have you can see the square and the dot, it is almost close. Some average curve we have taken, some small variation because you are taking spot measurement, and during that spot stabilization is another problem. Power supply has to be stable because you are sending constant current source, and that has to be stable. So, because of that minor fluctuation may be there. So, for measuring the TCR, so the second curve is plotted, is basically the derived curve from the first one, delta R by R, where R is the reference temperature or temperature resistance value, reference resistance, which is the resistance value at room temperature or ambient temperature, and delta R is the change. So, if you take the delta R by R ratio and the change of temperature with respect to the ambient is delta T, it also straight line, and from there you can easily calculate the alpha value, and that is obtained as 0.006064 like that. Now, the flow rate measurement, this is the setup which is used for measuring the flow, and here is the nitrogen cylinder, because we are measuring the nitrogen flow with just basically we can say it is a calibration curve. So, the flow of the gas is the gas flow, that is nitrogen is used, and from the cylinder it is a mass flow controller which can control the gas flow from the cylinder. The gas pipeline is connected to a tube, narrow tube, and inside the tube we put the sensor, and this is the sensor, and the PCB is here, the PCB fixed inside the tube at a particular point. This is a glass tube, and now this sensor point is connected to a constant current source, and now across these 2 points if you measure the voltage, then you can measure the change of voltage with respect to the flow, because you change the flow here, so automatically heat dissipation will be there, and if you send a constant current through that, so because of the heat dissipation the temperature of that particular tip will vary, and because of the resistance value will vary, and this resistance value if varies, then you will get a voltage drop, and that voltage change is because of resistance change, as we have sent a constant current V equal to IR. If I is kept constant, so directly V will be the proportional to R. If R changes, so accordingly the voltage drop also changes. We assume that I remains constant, that is why we need a constant current source. So, with this measurement setup, we measured the delta V voltage change for different values of the flow of nitrogen gas. So, that is measured for different nitrogen gas flow. Flow rate measurements are carried out with gas flow direction along the width of the sensor, that is structure 1, and along the length of the sensor, that is structure 2. Both the sensors are fixed inside the tube, and we measure the flow versus the change of the voltage. Flow we can measure by mass flow controller, which is connected at the mouth of the nitrogen cylinder. So, from there you will get the flow, and delta V you can measure from the voltmeter connected across the anemometer. So, now the delta V versus flow rate is this is the measured value for sensor 1, and sensor 2 is the structure 2, the delta V versus the flow rate. You can find here up to the 100 to 700 cc per minute, and here for sensor 1 the 50 to 300 you can get very linear curve. The nature is linear, and due to the minus delta V, because whether your resistance changes or resistance increases or decreases, depending on that, voltage will also change. Either positive or negative direction means whether it is increasing or decreasing, that will depend on the positive temperature coefficient or negative temperature coefficient. So, in case of metal, it will be the voltage drop will be less and less, because resistance change will be in such a fashion, so that you will get the sign because of whether positive or negative. Now, the flow rate versus the change of voltage, that may be the calibration curve, and later on you can use the similar curve, and directly from the delta V change you can measure the flow, you can estimate the flow, okay, from the calibration curve. Now, this is the anemometer principle. The second one is the differential temperature technique. So, in this particular case, two thin film sensors are placed symmetrically around the central heater on a micromachine diaphragm. Two additional sensors are arranged at the rim of the silicon chip for fluid temperature measurement. That is not changed, this additional sensor, and here we will use some Whiston's bridge, so that with respect to some reference resistance which are kept at the rim, we can see the change of the sensing element, and accordingly we can get the output by balancing a bridge which is the Whiston's bridge, and there you can get much more accurate measurement. Silicon nitride is used in this particular case to form the diaphragm of the micromachine flow sensor, because silicon nitride is a better insulation property than silicon dioxide in both in respect of heat and the electrical conduction. So, now here this structure looks like this. This is the membrane structure. Basically, here you are going to make 4 resistances D1, D2, S1 and S2. Similar, almost similar resistances you are made, and in the central portion is the heater. This is the heater portion, heater is here. This is the, because here in this particular technique the heater and sensing elements are different. Heater is placed at the middle, and the D1 and D2 is a far away from this sensor part, far away, so that it can measure these two resistance will basically the ambient resistance it will measure, and that since we are not going, it is far away from the heater, these two are not going to change. Okay. Now, this is the D1 and D2, we can call it as a reference resistance, and now the S1 and S2 are kept here and here. So, when there is steady state and no heater is there, so then all the resistances D1, S1, S2 and D2 will be the same. At the steady state under the ambient condition, no heating will be there, you are not heating, it is all kept at room temperature. Even then, if you and a steady state flow condition, what will be there? Both 4 resistance will be equal, and in under that condition the bridge will be perfectly balanced. Bridge will be perfectly balanced, output will be 0. Now, what is done here? The whole the 4 resistance along with the heater. Heater is nothing but is also resistance. Is put on the silicon nitride. The black region is a silicon nitride. It is not cross section. This top part is not cross section. Basically, it is like that. This is the thing you can see is here. Okay. So, now here is the top surface is shown, and the black region is basically the insulation layer, nitride on top of you are making these 4 resistances. Now, what will happen if you power the heater? So, during the flow from the heater the fluid will absorb the heat and it will flow in this direction. So, accordingly what will happen, this S2 will be the downstream, this S1 will be in the cool region and S2 will be in the hot region, because if the flow is gas flow is in this direction. So, now when the gas flow will be here, this will be from here the gas is flowing, heater, from the heater some of the temperature will be transferred into the gas, and the gas will be hot, and because of the gas this S2 will be at the hot region and this will be the cold region, temperature difference will be there, and because of that you will have the unbalancing the bridge will be unbalanced, because there S1 will not be the equal to S2, one is the downstream and another is the upstream. So, one will be in the cold region, other will be in the hot region. If the flow is more and more, so then more heat will be transferred into the S2, so that the S2 change will be more compared to the S1 change. So, the flow density, this gas flow velocity, depending on that, if it is a more, so difference of the resistance change S1 and S2 will be more and more. So, accordingly bridge will be more and more unbalanced. If you estimate how much it is unbalanced, so based on that you can have an idea of the flow velocity. So, that is the basic principle. So, now if you go for analytical analysis, then it is like that. Velocity distribution in a flow channel is given by continuity and boundary layer equations, and these two equations are given here. Del u by del x by del v by del y is equal to 0, where u and v as the velocity component along x and y direction inside the fluid medium. So, other equation is del u del x v del y equal to v in del d2u d y square del y square. The boundary conditions are like this, and where u is the velocity component in x direction, v is the velocity component in y direction, and v infinity is a free stream velocity. Is a free stream velocity means when the normal laminar steady state velocity of the fluid not in the x component and y component, y in x direction, normal free stream velocity is a v infinity. Now, the velocity boundary layer thickness is given by this, that because the velocity since there is obstruction, there will be a boundary layer will be formed, and this boundary layer, if it is the delta, then delta at x is a delta x will be given by 5 v infinity thereby, that is a free velocity by v x to the power half, and other will be 5 into r e x to the power minus half. R e x is the Reynolds number. The thermal transport equation can be written as this, and the ratio of the momentum and the thermal boundary layer thickness is given by del t is equal to P r to the power 1/3, and P r is known as the Prandtl number. Here is given P r, which is known as Prandtl number. Nu is the Nusselt number. So, heat transfer coefficient, which is convection in nature, convection coefficient can be calculated using the NUX, which is a dimensionless number, which is given by H L by K and is equal to 0.664 R E x to the power 0.5 P r to the power 0.343, where R E x is basically is a Reynolds number, is a rho V L by mu, and P r is Prandtl number, which is mu C p by K, where the rho V L mu C and P are given here. Rho is the density of the fluid in kg per meter cube, V will be the velocity of the fluid meter per second, L is the length of heated plate, mu is the dynamic viscosity of the fluid, K is thermal conductivity of the fluid, Cp is the specific heat of the fluid, R is the Reynolds number, Nu is the Nusselt number, and Pr is the Prandtl number. So, these are the relation. Based on those relation, you can do some simulation, and also we have tried to simulate the flow in a simulator, which is a Coventerware, is a renowned the MEMS simulator tool, and there two solvers are there for fluid flow. One is MEM-etherm and other is CFD, which is computational fluid dynamics. Two module is there. Using both the module MEM-etherm and the CFD, some simulation has been carried out and the results will be given. CFD is used for simulation of differential flow rates. The obtained flow fields are used in thermal analysis. The flow fields which is obtained from the CFD analysis can be used for the MEM-etherm analysis. Now, this is the structure you can see here. So, you can get this is the basically the heater in the central place. You can see this is a heater, and the 4 resistances are one here, and this is another here, and these two are wide apart from the sensing element, and this portion is the membrane. You can see this region is the membrane, this region is the membrane here, and here is the reference resistance is this region is 1 and this region is 1, is wide apart from the sensing, and the central is a heater. For heater there are 2 bonding pads, so you can heat the heater, and these are the upstream and downstream sensing element. one is kept, these are very close to the sensor, so that the heat will be directly transferred from this heater to the sensing element. So, you will get much more sensitivity if you can make this heater very close to the make the sensing resistor very close to the heater. So, now another structure may be thought of, there you can have the meander line of resistance, so that total surface area of the resistance is more, so that the change of resistance due to the heat absorption or heat fluid flow which converted into the heat change will change the resistance. That will be much more effective if the total area of the resistance is more, and that can be done by using the meander line resistances. So, that you can see, this is basically these two are heater bond pad, other 4 1 2 3 4 are the Wheaton's bridge. There are four bonding pad requires, 2 are the power supply and 2 are the output. Okay. So, all resistance are connected wired in such a fashion, the 4 resistance will fit into the Wheaton's bridge. Now, you can get, this is the Coventer wire 3D flow sensor structures. The whole structure, you have to define the structure in Coventer wire. So, this you can see the bonding pads are here, the total 6 bonding pads, and these are the resistances 1 2 3 4, and in the central is the heater. Here is the heater. This is generated by Coventer wire for simulation, and E-therm analysis has been carried out, and there the parameters are like that. For different heater supply currents, its temperature, resistance and voltage is noted, and initial resistance of the heater is 70 ohm and initial temperature is kept 27 degree centigrade. Now, these are the changes. Heater current, there is power supply to the heater, if you change from 8 milliampere to 10 to 12, accordingly heater resistance also will change, and heater temperature is 31.96 or 56 degree centigrade, 99 degree centigrade, that we can get from the E-therm analysis. And later on you can go for CFD analysis, the flow channel. There also you have to design the whole in a 3D structure of the whole sensor is to be done, and there you have to define the inlet through which the gas is flowing, and the heater location and the flow channel through which it is flowing. It is not looks like physically how you are getting it and how you are fixing it in the measurement setup, rather some hypothetical the structure you have to define into the simulator, so that it can simulate using the boundary layer technique, and again it will do some kind of the finite element or finite difference analysis to get the flow pattern. So, now the CFD analysis, the assumed channel is a 0.1 centimeter, 0.1 centimeter into 0.10 centimeter cubic structure is created, what you have seen. 3 patches for central heater and 2 diaphragm sensors are made at the bottom of the air channel. The heater temperature obtained from the E-therm simulation for 10 milliampere current is given as the input for CFD, and this 10 milliampere, what is the temperature that is obtained from E-therm analysis in earlier. The temperature distribution around the heater is studied for different conditions. These are the steps how to go for simulation. Gas flow velocities and the heater temperatures are varied, and this temperature distribution is analyzed in order to define the appropriate positioning of the readout sensor. So, these are required for designing, means the proper positioning of the sensor and the heater on the silicon surface, so that you can go for making the mask. So, these are some temperature distribution around the heater. The color chart is given by 104 degree centigrade, 480 degree centigrade. So, this is the heat distribution around the sensor. So, you have to have the choose certain location where we will put the upstream and downstream resistances. Now, here are some simulation results of the CFD. These are the flow rate is a cc per second, the upstream sensor, downstream sensor. you can see the temperature difference here is calculated. So, the downstream means the after downstream temperature will be more than the upstream. So, there is temperature is 39, here 43, here you can, if you go the, if you see the flow rate changes. So, if the flow rate changes, then you can find the temperature difference between the downstream and upstream also differ, because lot of dissipation will be there for higher flow rate. So, because of that, temperature difference from the upstream and downstream will be more and more, isn't it? Lot of flow means more heat is going to the downstream sensor. So, downstream sensor resistance is going to temperature is going to increase. So, that is why you see here 17.5, 66.1, here you are getting 48.6, and the beginning if the flow is low. So, both the downstream and upstream sensor temperature will be almost same, not much difference, from 3.6 to 4.6 to here 48.6 if the flow is 40 centimeter cube per second. Okay. Now, these are some simulated values, and those are plotted here. You can see this is basically cc per minute, okay, and here difference in temperature, this is a highly linear, after that it saturates. After it saturates means if the flow rate is very large, so then the difference of temperature is almost constant, but is low flow is from laminar flow you can get the linear nature, and this nature is useful for measurement of the flow. And E-therm analysis also you can get the distribution here, the flow rate upstream and downstream of Wheatstone's bridge, because after that you are getting Wheatstone's bridge output. Earlier you got the temperature difference, now that is reflected into the resistance change, and after that if you have supply of the bridge is constant, then you can get the offset voltage, and that you are getting here. So, with different flow rate, what is the Wheatstone's bridge output voltage, that is given here. So, that plot is also shown here. You can see this also up to certain flow it is linear, after that it saturates almost. So, this linear region is may be used for the flow sensor of this differential temperature technique. Now, here the fabrication steps are almost similar to other one. First you have to grow the thermal oxide, and then photolithography of the front side oxide, then photolithography and patterning of the back side oxide. Only difference here, there it was single resistance, but here you are using 4 resistance along with the heater. Now, the step 4 is thermal evaporation chromium nickel film, then pattern it, then you deposit chromium gold film, then pattern it, and last step is the backside etching of the silicon substrate from the diaphragm structure to get the diaphragm structure. So, that is the total fabrication step. And now, these are the two structure, one is a rectangular shape, another is a meander line shape. Meander line shape will be much more sensitive. What is the difference? As I mentioned few minutes back. So, you see here. So, this is portion and this portion resistance are meander line, here is only straight line, one single line. So, here you can say 3 lines, all the 4 resistance in the layout are same, 1, 2, 3, 4. So, here only the meander, here is the single line. Okay. So, that will be much more sensitive, because total area of the surface area of the resistance are more here. So, these are the mask layout of all the layers you can see here. So, thank you very much. Let us stop here today.